Action. Hello and welcome back to Calculus 1, section 4.2 on first and second derivative tests. So chapter 4 is all about applying the derivatives. And this section, so first section was min and max, right, which focused on finding a way to find the extremas of the function, the minimum point and the maximum point, because we want to know maximum profit, minimum cost, maximum or minimum pressure or whatever, right? So we have reasons why we would look for extreme points. So that was 4.1. Now in 4.2, we want to look at other qualities of the function. For instance, function is increasing, decreasing, is concave up, concave down, and all of these other things, including min, max, critical points, and inflection points. So everything is in this one section. So I'm going to first explain the entire section with one graph, and then we are going to take a look at calculations on how to deal with this. So I'm just going to draw function f of x and put over here x-axis to emphasize that all of the answers that we are getting here are going to be x values. So we're talking now about intervals. Interval, let me just write that actually here in blood. Interval is going to be either x1 to x2 or x1 to x2, right? So it's not x comma y, it's not a point. Interval is length on the x-axis for which something happens with a function. So when we are talking about interval of time, this class is well, it's suggested to start at 10:30, and suggested end is 1:15, right? So what's the interval? It's 10:30 to 1:15. So you see it's time, comma, time. So same units. All right, so what do I have here? Well, first off, let's deal with stuff we already know. This point over here is going to be relative max, right, or local max. So I'll call it relative max, because it seems that this side will go forever up and there will be higher points than that. We also dealt with this point here, which is a relative min. Now I will place those at A and B location. Okay, so now we know that these two ends are going to negative infinity and positive infinity on the x-axis. So I labeled everything that was important. Now, we read from left to right. Therefore, we are going to read this graph from left to right. So imagine yourself walking from left to right. What do I have? Well, over here, I have the increase, then I have a decrease, and then I have the increase again. Right? So the function is increasing because I'm walking up the hill, then it's decreasing because I'm walking down the hill, and then it's increasing again walking up the hill. So we need to develop mathematical procedure which will tell us, without looking at the graph, where the function is increasing, i.e. growing in value, and in y value, and where it's decreasing, i.e. getting smaller, right, in y value. Now, there is also notation here that we are going to use. I'm going to say that f of x, right, is increasing on negative infinity to A union B to positive infinity. So as you can see, I have the interval from negative infinity to A. So for all of those x values between negative infinity and A, the function is increasing. And also, for all x values between b and positive infinity, function is also increasing. Now, I also have that f of x is decreasing on a to b. So function is decreased. Now observe that I'm using open intervals. So these intervals do not contain point A or point B. And the reason for it is you can't be increasing or decreasing at a single point. That makes no sense, right? You have to be at point in space and then go to higher elevation, which is another point, or a lower elevation for another point, right? So it's not, we are not going to use included brackets because, again, we can't deal with increase, decrease at the point. We have to deal with it over the interval on the open interval. So that's one concept that we are going to study. And please note that when your increase changes to decrease, you have a max, and when your decrease changes to increase, you have a min, right? And that should also be common sense as we move on. The second part of this would be in blue, concave down and concave up. Now I have to find arbitrary over here somewhere point C. So now I will say that f of x is concave up, or actually concave down first, because it's first on the list, from negative infinity to C, and f of x is concave up C to positive infinity. Point C is called inflection point. And that's where the concavity changes from up to down or down to up. Another example of that would be x cubed. We'll deal with it when we get there. So this is the entire thing that we are learning today. You have part of a function that is increasing, part that is decreasing, then you have some concave down and concave up parts. So now let's take a look at the first. Actually, let me also make it clear. Maybe I can use, let's use whatever this color is, dark red. So this is going to be first derivative test. And this is going to be second derivative test. So we have a first and second derivative tests. So now let's go and learn the first derivative test. Also known as FDT, right? I don't want to spell it out every time I need it. So FDT. Well, we are going to start with a statement, and then we're going to take a look at examples. This is just a procedure. There is no theory over here. We see, right, using our eyes, right, that for the increasing function all the slopes are positive and so on. So I'll write that down, but we just have the procedural stuff here. So if f prime computed at C, or let's use A, if f prime computed at A is larger than 0, then f of x is increasing on that interval. If f prime or A is less than 0, then f of x is decreasing on that interval. A is the test point. A is any test point. A is any test point in the interval. Now, in blue, I'm going to write this down and then explain later. Partitioning is done by critical points and vertical asymptotes. All right, so let's take a look at an example of this monstrosity. So I will pick something from homework, and you have additional exercises worked out in a textbook, obviously. So let's take a look at, say, problem 22 to understand what's happening here. So I have f of x is equal to x to the fourth minus 4x cubed plus 4x squared. Let's hope it's a good example. If not, I'll just switch it. All right, so what do I have? Well, I know that in order to do the first derivative test, I need to find the first derivative first, right? So that should be 4x cubed minus 12x squared plus 8x. And I also said that the partitioning, I don't know what that means yet, partitioning is done by critical points. Oh, okay, well, that's procedure from yesterday. Set it equal to 0, find critical points. Great. I can factor out x. Sorry, I can factor out 4x. Gives me x squared minus 3x plus 2 equal to 0. From where 4x equals to 0 and x is equal to 0, that's the first one. The second one will factor over x minus 2x minus 1. So I have x is 2 and x is 1. Nice. I have 3 critical numbers, and then we can find y values to become critical points. So these are the critical numbers. All right. This is the work from yesterday, nothing new. Here is the new stuff. First derivative test starts here. I'm going to draw a line and partition that line with critical numbers that I have. So the first one is 0, 1, and 2. I do not have any vertical asymptotes. So negative infinity on this side, positive infinity. This is x-axis, right? So this is me partitioning the whole thing using the 3 values that are there. Now, I am going to, in red, pick test points in each interval. All right, so -1 is good one, 1/2, 3/2, and 3. So when you can pick a cheap point, right, you pick a cheap point. Now, the number to pick between 0 and 1, well, you can also pick 0.3791165, but then it will be a little bit interesting to compute with that thing, right? So you just pick whatever easiest you can, right? Now, what I said here is, look, if the derivative computed at the point is a positive, the function is increasing. If it's a negative, then the function is decreasing. So my job now is to use the derivative and compute these test points. So I need to compute f prime of -1. So that's going to be, I'm using the derivative, 4 times -1 times -1 squared minus 3 times -1 plus 2. This is the derivative. So I'm just going to point the arrow and say f prime of x equals 4x times x squared minus 3x plus 2. That was our derivative. It's right on the top of the screen, which is the reason why I'm not scrolling so much up. I needed to see it, right? So now I can scroll up. I need to compute this. What do I have? I have negative 4 times, this is 1 plus 3 is 4 plus 2 is 6, which is negative 24. So it seems that the function is decreasing over here. That's less than 0. Negative 24 is less than 0. The statement up there said if the derivative computed at the test point is less than 0, you have a decreasing function. So I draw the arrow for a decrease. The next one is f prime at 1/2. So now we have 4 times 1/2 times 1/2 squared minus 3 times 1/2 plus 2. You actually don't have to compute all the way to negative 24. If you can make argument that something is increasing and decreasing before you actually do all of these things, you do it, right? So half of 4 is 2, and in parentheses I have 1/4 minus 3/2 plus 2. So I hope you see that this part is positive. See, this is the part of the analysis that I want to use. I don't want to compute these things because I really don't care what number comes out. I just need to know if it's positive or negative, because that's all I need, right? If the derivative is positive, it's increasing. If it's negative, it's decreasing. So that's all I need. Now, how do I know this is positive without calculating? Well, 2 is bigger than negative 1.5. And then I have to add a quarter to it. So it's positive. So positive times positive, this is bigger than 0. So the next part is increasing. Then we go and do f prime of 3/2, which is 4 times 3/2. And then I have 3/2 squared minus 3 times 3/2 plus 2. All right, so this is cancel. So it's 6 times. I have 9/4 minus 9/2 plus 2. Well, now 9/2, that's 4.5. So that's bigger than, this is almost a half plus d, right? So this is almost a 5. And this together is about 3.5. So negative is bigger. So this whole thing is negative. Now again, take the calculator, punch everything in if you care, and you will get values. So this is now decreasing. And finally, f prime at 3 is going to be 4 times 3. And over here we have 3 squared minus 3 times 3 plus 2. 3 squared is 9, minus 9 is 0, so the whole thing is 24, which is larger than 0, so we have increase. Again, this is what your first derivative test is. So what you see on the screen now is the first derivative test. Stuff prior to that was looking for critical points, which is from the previous section. So what is the first derivative test? The first derivative test is going to help you figure out when the function is decreasing, when is increasing. So it looks for intervals of increase and decrease. It does that by partitioning the entire domain of a function through critical points, critical numbers, and vertical asymptotes. Now, we did not have any vertical asymptotes in a polynomial, so we didn't include any vertical asymptotes in this case. Next problem I do, it will have vertical asymptote. So what we did is, once we do partitioning with critical numbers and vertical asymptotes, we pick values from each of the interval. I have the interval from negative infinity to 0, then I have the next interval from 0 to 1, then next interval 1 to 2, and then 2 to positive infinity. From each of those intervals, I pick any point I want, right? It has to be in the interval. You can't put 100, right? You can't pick 100 between 0 and 1, right? So make sure you don't do that. You can pick 1 over 100. That's okay, because 1 over 100 is 0.01, and that's definitely between 0 and 1, right? So sure, you can pick fractions, you can pick, even you can pick e to the exponent, because that's going to be useful when you do the ln problems of this type, right, for calculation purposes. But now, since we have all the basic, this is a very basic example, I pick -1/2, 3/2, and 3. And then it's important to know that we are computing those test points in the first derivative. Please say it to yourself loudly. First derivative test. You're plugging stuff in the first derivative, right? Now, if you want to know the y value of the point, you plug it in the original equation to get comma y, right? So now I'm taking my test points, plug each one at a time. Sometimes you have 2 test points, sometimes you have 15, right? Whatever amount you have, plug one at a time in your first derivative, and you will get numbers that are smaller than 0 or larger than 0. Now, if by some accident you actually compute this and you get 0, well, you missed something, because you just found another critical point that you didn't have on your list. This calculation can never end up being 0, because that's how you obtain the breakpoints for your intervals. You set the first derivative equal to 0. And then that pretty much guarantees that if you did everything right, these calculations will never be 0, right? So they will always be less than 0 or larger than 0. Now, at the end, no one cares about the numbers you actually get. If you are able to claim, from over here, you should be able to claim, negative times positive is negative. Negative numbers are smaller than 0. There's no need to calculate all the way. So if you can make arguments and skip some calculation, that's great, because you're saving on time. Your job is to figure out which of these are less than 0 and put decrease for those, and which are higher than 0, put increase for those. Now, you know, this being a simple example is also a dangerous example. I need you to remember right now that this beautiful up-down situation that you have going over there is just by stroke of the luck, okay? Think about, well, it happens because it's polynomial, right? It's not the luck, it's polynomial, and polynomials will have stuff like that. But if you have a different type of a function, if you think, like, consider 1 over x, which we are going to do, well, I mean something similar to it now, that one is always decreasing, right? So you will have arrow down and arrow down. So 2 consecutive down arrows and no up arrows, because that function is decreasing on both of its parts. Think of e to the x, a continuous stroke up, right? So that one will only have 1 interval, and it will always be the arrow up for the whole thing. So please don't memorize that you are supposed to alternate these. No, 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 right? That only happens for polynomials. But as soon as you introduce anything else, the whole thing goes. Now, calculated critical numbers, did partitioning, did calculations, populated my arrows, and it's finally time to write the answer. Do you want your full points? Well, you better write the answer to the question. Let's do it green. Whatever. So what's the answer? The answer is f of x is increasing on, and then you go look for your up arrows. So 0 to 1, union 2 to infinity. F of x is decreasing on negative infinity to 0, union 1 to 2. Guys, this is your answer. This is what gives you points at the end of the day. Everything prior to the green is partial credit. So make sure that you actually finish the problem by writing the answer, clearly stating intervals of increase and intervals of decrease. And those better all be x values. So x is 0, 2x is 1. Like your interval on time. I'll see you between 2 and 3, right? Interval of time, 2 or 3. Or when they're giving you the estimate of when they're going to come in and fix something in your house. Well, we'll see you tomorrow between 10 and Thursday next week, right? Because that's the best estimate they can give you. And then you have to take off for like 2 weeks. So the answer is that. Now, what do we get for free from here? We did all these calculations. We found our answer. We boxed the answer. We have 100% of the points. Yay, right? So this is your problem on your next exam. Find the, right, do the first derivative test, and here is the function, blah, right? And you box this and you're done. What do you get for free? Look. Look at these arrows and the way they're organized. We know that on critical numbers and critical points, we have min or max values, right? Do you see that you get for free which one is which? Do you all see a minimum at 0? If you don't, I'll lend you my lenses. Right? There is a minimum at 0, maximum at 1, and minimum at 2. Because it has to decrease into a minimum and then increase out of it. So that's a min. I don't know its y value. I can find it. All I need to do is to put 0 in original equation and get the y value. Right? So I don't know the point until I compute the point. But I know it's a min. So I can add. So let me write here on the bottom. I get min max for free. In parentheses, look at the diagram. Next one, compute y values for each min max in parentheses by using original equation, by using f of x, y equal f of x, whatever. I don't know. Bam, done. Great. So you get that for free. That's awesome. Let's do another example. Guys, the best part of this lecture is when we go to the second derivative test. Is exactly the same calculation, just off of the second derivative. We're not going to do anything different. You are going to set the second derivative equal to 0, and instead of calculating critical points, you'll be finding inflection points. Partition it on inflection points and vertical asymptotes, and do the same analysis. Test point less than 0, concave down. Test point larger than 0, concave up. So it's going to be literally Control-C, Control-V, and then just change the terminology, right? You're going from first to second derivative. That's it. All right, let's do another one of the first derivative test. I want to use something a bit spicy. It has to be spicier. Let's go with f of x is equal to, say, 6 over x plus 2. Right, that's our function. Okay, great. Now, this is where your knowledge, right, ancient knowledge kicks in, because you need to know that vertical asymptote is at 2, otherwise you are, or negative 2, otherwise you are doomed. So we know that the vertical asymptote at x equals negative 2. Again, do not write VA equals negative 2 because that triggers my allergies, and then then my eyes water up, and then I can't like you anymore because you're distorted in my vision. Kind of blurry. So we have that the vertical asymptote is at -2. Now, I still have to do all of the stuff, right, which is the first derivative and equal to 0 to find critical numbers and so. So, first derivative, no coughing, of x is equal to, and we do the derivative. Now, it's going to be -6 over x plus 2 squared. That's the derivative. You can go ahead, use the chain rule. You can go ahead, the quotient rule, or you can just use the chain rule, which would be better. You just take x plus 2 up with a -1 exponent and then just plow through that. Good. Now, you set this equal to 0. And when you cross multiply, 0 will kill the denominator and you get -6 equal to 0. No solution. Now we know that that means no critical points. And we also know that that means no min-max. Now I ask you for the first derivative test. No critical points. What now? Well, fear not. We have a vertical asymptote. And even if we did not have a vertical asymptote, the entire domain would be just one partition, pick any point. Right? So it doesn't matter. You don't have to have critical points because functions do not have to have min or max values. Like e to the x doesn't have min or a max. It's always increasing, right? Or a linear line, y equal x plus 7. Also no min or max. It's always increasing, right? So it doesn't matter. If you don't have critical points, if you don't have vertical asymptotes, the entire domain will be just one partition and you pick any point in there. But for this particular problem, we do have partitions because there's a vertical asymptote at -2, which breaks my -infinity to +infinity into 2 parts, and I just need to pick 2 values. Now, clearly I'm going to pick 0 on the right-hand side because that's always cheap to compute, and on the left-hand side I can pick anything, so I'll pick -3. All right. So first derivative computed at -3 is -6 divided by -3 plus 2 squared. That's -6 over positive number. Look, denominator is squared. I don't care what is happening in the denominator. It's squared. Every number that you square is going to end up being positive. Because if you square 3 by itself, right, 3 squared is 3 times 3, which is +9. If you square -3, you get -3 times -3, which is +9 again. So as long as you have the even exponent in the denominator, it's going to be positive. So what do I have? I have a -6 divided by the positive number. That's negative. I didn't even compute the value. I don't care. Negative numbers are less than 0. That's a decrease. And we move on to the next calculation. 0. I have -6 divided by 0 plus 2 squared. I know, easy to compute, but I don't care. It's -6 divided by a positive number. Negative divided by a positive is negative. That's less than 0, another decrease. And here is the example. As I said, you cannot memorize alternating arrows. When arrow is followed by the same arrow, you cannot have min or a max at that point. Well, you know it's a vertical asymptote anyway, but, you know. So, what's the answer? The answer will be f of x is decreasing on -infinity to -2 union -2 to +infinity, and we are done. What do we get for free? Again, min, max, but we know there aren't any because we didn't have. All right. So I like to do one more example with some more exotic functions. And then we can go and do the second derivative test, which will be the same calculations, except we're going to associate different terms and different meaning to the whole thing, but it's the same thing. All right, so what should we do? We have the choice of the inverse tangent, some square roots. X squared minus 2ln x. That looks evil enough. How about that? Sounds good? Yeah, that one. I'm excited. Anyone? You guys are terrible. All right, so problem 34 says f of x equals minus 2 ln x. This is our function, right? The procedure is always the same. First derivative, critical points, right? But you know what I'm going to do first now, since we are not in a polynomial realm? I'm going to do domain first. Because I have ln x in it, right? And that's going to cut the good old negative infinity to positive infinity into 0 to infinity, right? Because you cannot plug in negative numbers into ln x. So I'm going to start at the domain on this problem and say it's 0 to infinity. So that way I don't have to worry about negative numbers at all in this problem because of ln x, by courtesy of ln x, okay? Now, let me just write this and then I'll erase it. Ln of absolute x would allow for negative numbers, but it will still kick out 0. You have a vertical asymptote at ln x at 0, whether it's ln x or ln absolute x. And you are going to run into absolute x once, so that's what I'm talking about. So, our domain now is only positive numbers because negatives are not allowed without absolute value. If you have absolute value, you still have to kick out 0 out of the domain because there is a vertical asymptote there. So we also know that there is a vertical asymptote, now that I spoiled it, right? We also know that there is a vertical asymptote at x equals 0. All right. Now we can do the first derivative and see what we can calculate. So f prime of x is equal to, what's the derivative of x squared? Very good. And what's the derivative of ln x? Excellent. All right. So we have our first derivative to be 2x minus 2 over x. Now we set that equal to 0 to find our critical numbers so we can do the partition. Well, to solve this equation, move 2 over x to the other side. So we have 2x is equal to 2 over x. Divide both sides by 2. We just have x equals 1 over x. Move x to the other side. We get x squared equals to 1, from where x equals plus minus 1. You see that the calculation is giving us a negative number, but we know better, right? Domain is 0 to infinity. Kill the negative number. So x equals 1 only because domain. And you go fix English later. So now I have my partitions. I can start first derivative test. Observe that I am starting at partition 0. It's going to go to positive infinity. And I am partitioning at 1. Nice. What am I computing? Right? I am computing the derivative. The derivative is right here. So the numbers that I am picking as test points are 1/2 and 2. So now the first derivative computed at 1/2 is going to be 2 times 1/2 minus 2 over 1/2, which is 1 minus 4, which is -3, less than 0, decrease. F prime of 2 is 2 times 2 minus 2 divided by 2, which is 4 minus 1, which is +3, larger than 0, increase. All right. What do we get for free? Minimum at 1, exactly. Let me do that first. I'll call it free. X equals 1 is a minimum. Actually, no, that's bad. Bad phrase. Minimum at x equals to 1. And then I'm going to calculate the y value for it. So f of 1 is the original problem, which is 1 squared minus 2 ln 1. And that's 1. So minimum is 1, 1. So that's for free. All right, let's write the answer and move along with our lives. So answer to the question up there is f of x is decreasing on 0 to 1. F of x is increasing on 1 to infinity. You can actually include minimum in this answer if you want to, right? It's what we get for free. But that's our answer. Hopefully when you review these 3 problems, you will see that all 3 had exactly the same structure. On the last one we did find the domain as well, but yeah. So look for critical numbers, look for asymptotes, look for domain. So that's that preliminary work. Then you do the partitioning and pick your test points. And then finally, the last step is to calculate all the test points in the derivative to figure out increase-decrease regions, and then write the answer at the end, and you're done. It's a very systematic procedure. Again, it tells us a very important thing, right? Very important thing, which is I'm going to go and look at the graph of, let's say, which company should we look at the stock? I'm sorry? MDT stock. All right. There you. Okay. So, oh, you can't see it. I'm clicking over here. Can't see anything. All right. So 5 years of Medtronic PLC. If you look, their stock started being about $53, and it's currently $86, right? So if you bought, so that's what, 53 and 86. That's 33, right? $33 difference. So if you bought this stock 5 years ago, right? You bought, let's say, 1,000 shares. It will be 1,000 times 33, and that would be the current worth of a stock. So what's the money that you made? It's the money that is the difference, right, times the good. So what do we get from here? Increase, 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 collapse. Increase, 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 fail. Increase, 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 fail. Increase, 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 fail, right? That's your increasing and decreasing functions, right? And obviously, we observe those, right, on the graph, and we know where it's increase and decrease. You look the 1 year, the 1 month, 5 days, and today. Now you would go, oh, sell, sell, sell. No, that's 80 cents. It looks terrible, right? It looks terrible, but that's 80 cents drop from 86.8 to 86 flat. That's 80 cents. So, looking at the history, should be fine. All right, good. So that's the reason we are looking at. That's the reason why we are looking at the increase and decrease, and we want to understand increase and decrease, and then we get min and max for free. The next order of business is to take a look at the second derivative test, which has identical procedure with new words and obviously off of the second derivative. So now let's look at the second derivative test. S dt. And first, motivation for this concavity business. Sure, when I explained it on the top, the first function I drew was like, whatever, right? But now, do we have business people in here? Anyone? Business, economics? All right, good. Perfect. This question is for you. So I'm going to put 3 portfolios here. X-axis is time, and y-axis is money, which is why I needed you. Now, we are going to start with the same investment of, let's say, $1,000, okay? So at time 0, which is today, or I don't know, a year ago, we started with investment of $1,000 on the account, and then the time goes and the money is going to change in value. Now here are the 3 graphs. Where do you want your money? 1, 2, or 3? We can start by asking a question: in which of those accounts the money is growing? 3? Can you tell me all of the accounts in which the money is growing? All of them are growing money. Very good. All of these accounts are growing money. What are we talking about? So all of the 3 accounts are growing money. Perfect. Where do you want your money? So does it matter where we put the money? It's going to grow. Oh, it does matter where we put the money. Okay, so where do we put it? 1, 2, or 3? 1. You want it in 1? Okay. You want 3? All right. Anyone else? Where do you want your money? 1, 2, or 3? You have to answer now, since you identified yourself as a business. economics and all that stuff. So where do you want your money?
I go with 1.
You want with 1? Okay. Anyone else? Not that no one gave me a reason why they want it there. It's just
1 is like a steady increase.
Yeah, that's what I thought too.
steady increase of money. Okay.
And 3 is kind of just like, it's not steady. It kind of stays the same, and you get no money, and then you just have a rapid growth. I'd rather have a steady growth.
You would rather have a steady growth.
Yeah, because I mean, like at 1, 2, and 3, it's not really growing until that. Growing that little bit.
This is why we have to have math courses. Your slope over here is going to be 1.
Yeah.
My slope over here is going to be 10. Who makes more money? Yeah, right? We want to put the money in the 3. This is the winner right here. Now, this is no concavity. This is concave down. And this is concave up. And for this particular application, concave up is the winner. All 3 accounts are growing money. The third account is growing money at the fastest rate. Okay? So, let me put this into another framework. You are driving to school, and your 2 friends are driving to school. You are all leaving off of the same parking lot, and one student is going to start, and everyone starts at the same speed. Let's say we start measuring at the same. So everyone has a running start, and let's say we start measuring whatever the start point is for measurement. Everyone is driving 20 miles per hour, right? Now, the speed for the first one is going to remain 20 miles per hour forever. The second one will be accelerating, but kind of slowly accelerating. The second one is going to go 30, 40, 50, 60, 70, 80, 90, 1,000 miles per hour, because in a rocket, obviously, right, going to school, because this is where the knowledge is. Right? Right. Yeah, that's why you race to school. I always understood when you get the speeding tickets when you're coming to school. I don't understand speeding tickets going away from the school, because you're just leaving the knowledge. And you should be depressed driving like 5 miles per hour. It's like, school is done for the day. Right? No tickets. You get the ticket for not driving as fast. Apparently in South Carolina, the speed limits, the highway is minimum speed limit 45, maximum speed limit 75 on the interstate highway, which is still not as cool as Autobahn in Germany. No speed limit. So, yeah. One of my friends used to work as test engineer for prototype cars, German cars. So his company was contracted by all the companies to test their designs on air conditioning. So this poor guy had to drive prototype cars, so that's the next year's or in the 2 years models for Audi, BMW, Mercedes, and so on the Autobahn from Germany to Italy, testing air conditioning. What a sad life. You go on a highway, you just drive like 200 miles per hour, then you stop, refuel, company paid for everything, right? No one even seen the car as a concept. People have no clue what you're driving because that car is not out yet. It will be out in 2 years. So a very, solitary life, I would say, right? So second derivative test, Is it? I don't know.
If the air conditioning is working.
If the air conditioning is designed well. All right. I'll tell him to watch this lecture because he's been mentioned. Zdravo, Peđa. I added a part. All right. Let's go with a statement now. If second derivative computed at a is larger than 0, f of x is concave up. If second derivative at a is less than 0, f of x is concave down. X equals a will yield a f of a, which is inflection point. Inflection point is defined as point at which concavity changes. Concavity can also change on the vertical asymptotes. So partitioning is done with inflection points and asymptotes. Please remember example 1 over x. 1 over x will have no inflection points, but concavity will change from concave down to concave up, right? Piece that spills the water and a piece that holds the water, right? U shape is concave up, and it holds the water if you dump the water in it. And then the other one is concave down, it goes downwards, and that one spills the water. So for 1 over x, if you think of the graph in your head, right, 1 over x has a concave down piece on the left and concave up piece on the right, and we had the vertical asymptote in between. So now we're going to say partitioning is done by inflection points and vertical asymptotes. So partitioning is done by inflection points and vertical asymptotes. So for the second derivative test, again, you have to find the first and the second derivative, set it equal to 0, get inflection points, see if you have any vertical asymptotes, then do partitioning, and then do the test, write the answer, and win. So let's go with a vanilla problem first. So f of x is equal to x cubed minus 6. This is problem 74 in the textbook. No vertical asymptotes, and domain is negative infinity to positive infinity, right? All real numbers. That's good to have on a side. Now it's polynomial, so we don't care about it, but for later. F prime of x is 3x squared. Please don't work out stuff for this, because that's the first derivative test. We don't care about it. We are moving now to the second derivative test. 6x. And this is the one you set to 0 to find x equals 0. Inflection point. It's not a point, it's inflection number, or it's just x coordinate. Inflection point is at 0, negative 6. Because you plug that 0 back in original equation to find the y value. So inflection point is at 0, negative 6. So now we do partitioning. The only partition that only number that partitions here is 0. Your inflection point. You still have your negative infinity or positive infinity on the x-axis. Pick any two test points before I die. Let's finish at least this one problem. There we go. So I have two test points, and I will do the second derivative test at negative 1, which is 6 times negative 1, which is negative 6, which is less than 0, which is concave down. Concave down. And second derivative at 1 is 6 times positive 1, which is positive 6, which is larger than 0, which is concave up. The same procedure, right? Different words, different meaning, but the same procedure. Do we get anything for free? Yeah, we get min and max again for free. Because we know if this is concave down has to look like this. And concave down will have max. So whatever critical number you have in this region, that critical number will be a max. See, I don't know where that is, but I know there is a maximum point somewhere right to the left of 0. And I know there is a minimum point somewhere to the right. Now, when you do the problem in order, you will also find your critical numbers and so on, right? So if you find critical numbers, and if there is a critical number in here, it must be a min. No, it's concave down, max, and this one concave up has to be a min. So we do get min and max free again. Answer, and let's move to the next problem. So answer, right? You want your full points. F of x is concave down on negative infinity to 0. F of x is concave up on 0 to infinity. And that's that. All right. So now we have this, and let's do a different example for secondary. We haven't done anything with ease yet, right? So maybe this problem. Let's work with the 78 and see what spawns out of there. They say p of x, f of x, whatever, it doesn't matter. X to the fourth e to the negative x. Second derivative test, right? So we want to know the concavity. All right, so we can write this as x to the 4 over e to the x and unleash the chain rule, right? So, I mean the quotient rule. So, p prime of x, the first derivative, is going to be e to the 2x. Then we have e to the x, 4x cubed, minus x to the 4, e to the x. Then we factor out e to the x, x cubed, and what's left is 4x minus 1 divided by e to the x times e to the x. So we can kill one of these. It's actually better if we leave it multiplied, because we have to take another derivative. If we were setting equal to 0 there, you want the factored numerator, so you can set each factor to 0, right, and get your critical point at 1/4. But since we have to take another derivative, it's better if you leave it as 4x to the... Oh, I was supposed to factor out... No, x cubed, that was good. I just have it wrong. It's 4 minus... I factored wrong. It was 4 minus x. All right. But leave it in the 4x cubed minus x to the 4 and now over e to the x, because I have to take another derivative. So p double prime is, and now take the derivative here. I have again e to the 2x, and then e to the x, and then the derivative of this is 12x squared minus 4x cubed, minus, copy the top, which is 4x minus x to the 4 times e to the x. All right, there we go. Oh, this is shaping to be a lovely problem. So the second derivative is factor out e to the x, and then just pile up everything here and add and subtract what you can. And then we are going to factor because we have to. I'm breaking up this e to the x so I can kill one. There we go. Now, this is 8x. Okay, so what can I kick? I can kick x squared, right? That's it. I can kick x squared, and what's left is 12 minus 8x plus x squared divided by single e to the x. Great. Now, set that equal to 0. When you cross multiply, denominator always dies, right? So we just worry about x squared, and then x squared minus 8x plus 12 equal to 0. So x squared equal to 0 gives me x equals to 0. Fine. And the second one factors over, or it doesn't factor at all. So what two numbers multiply into 12 and add to 8? Do any? Factor. -6, -2. Thank you. So x -2, x -6 equal to 0. So x is 2 and x is 6. Beautiful. Second derivative test. Let's go. Partitions. 0, 2, 6. Test points. -1, +1, 3, and 10. Whatever. You can pick 7. It's just awkward to compute with 7, so pick 10. You can pick 7.3 if you want. It's fine. Pick whatever. Whatever makes you happy, right? This is a math class, so your happiness is highly valuable and important to us. All right, so I'm going to copy the derivative over here so I can actually see it. So I can scroll. Actually, no, I'm going to show you the best way to compute this. So here's the factored form. Great. All right. P double prime of -1. Okay. The denominator is always going to be positive because domain range of exponential function are always positive numbers. So denominator can only give positive results. So we don't have to worry about it. Also, x squared always gives positive results. So we don't have to worry about that either. The only thing we have to worry about is x minus 2 and x minus 6. So I'm technically just looking at -1 minus 2 times -1 minus 6. And that is negative times negative, which is positive. So concave up on the first. Second derivative of 1 is going to be 1 minus 2. and 1 minus 6. That's also negative times negative, which is positive. So another concave up part. Second derivative computed at 3. Well, that's going to be 3 minus 2 times 3 minus 6. And that's positive times negative. And that gives me a negative, which is less than 0, clearly. So that's concave down. And finally, second derivative computed at 10 is 10 minus 2, 10 minus 6. Both of these are positive. When you multiply two positive numbers, you get a positive. So concave up again. Now we want to write the answer and go for lunch. F of x is concave down. Is the first one down? No, concave up. On negative infinity to 0, union 0 to 2, union 6 to infinity. 3 concave up pieces. F of x is concave down on 2 to 6. In preparation for your next section, which is 4.3, you are going to have this as a part. So after exam tomorrow, we are going to go through the 13-point problem. You will be looking for domain, x-intercept, y-intercept, horizontal asymptote, vertical asymptote, slant asymptote, critical points, inflection points, first derivative, second derivative, first derivative test, second derivative test, and then graph the function. That is your 13, right? So 13-point step, right? 13-step procedure to graph function by hand. But you know what? It's long, but you get to graph anything. So someone can throw at you ln of cosine squared. And you say, that's not a problem. You just do some calculus on the side, some derivatives and these things, and you will be able to graph it by hand. So I'll see you tomorrow. We start with the exam, first thing in, and then after the exam, graphing. Bye.